Welcome, everybody. My name is Ammoun. I'm a research engineer in INRIA Rocquencourt, and I will present today a tool that had been created at École des Mines de Paris with Fawzi Nashashibi and Alexandre Bargeton. So the presentation will be, the tool is for a new geographical information system for ADAS-oriented application. I will begin my presentation by introducing the motivation for this work, and I will present then the Caorto, which is the name of the GIS. I present the database structure, the attribute that we have added to the map, and a quick introduction to the functionality of the GIS, map builder, the map explorer, and the map updater. I will briefly also present and describe the usage of this tool into two projects in which we are involved. So about the motivation. I think we all agree that the geographical information system has a central role and position in all ITS applications. I'm coming from a domain when everybody work on environment perception, control system, and of course everybody want to know some information, some static information about the environment in a way to conduct the perception or the control system. There is many projects who was aiming at defining the next generation of maps, like Next Map, Act Map, Safe Map, but they were from the year 2000 till now. But for the moment, we didn't find a suitable solution, I would say commercial solution, that can answer our need as designer for ADAS application. There is another way. All the research projects, most of them are assuming that we have this kind of maps, so we need it now for some project, from research project. There is some inconvenience for current GIS. It's mainly the lack of attribute, I would say advanced attribute for the road, and at the same time it's the rigidity of the existing GIS, in which we cannot add new type of attribute, parameter of the road. I would say by attribute, parameter of the road. The lack of precision of the attribute and of the map itself, and the high prices for the solution that does exist. Our work was synchronized with other initiative for opening the map industry, I would say, like the European Inspire Directive, which is aiming at standardization of the sharing of spatial information in Europe, and the OpenStreetMap, which is a collaborative tool. In two words, I would say that OpenStreetMap is the Wikipedia of the roadmap. So it's a collaborative tool, it's a web portal, and everybody can participate to it. Government, private sectors, I would say like Yahoo, for example, who gives an access to its satellite images, and of course everybody can participate to it. So there is mapping party between people, everybody can participate and do its own mapping of the road that he wants by adding road name, road attribute. And we have seen the importance of such a solution, for example, during the Haiti earthquake, when all the data of the disaster was done in real time using the OpenStreetMap data. And one thing is important, that we can export the data created by users under the Creative Commons license. So talking about Caorto Architecture, so it's based on, we export data from OpenStreetMap. There is two ways. We export data from OpenStreetMap or our own GPS track data. It's an input for our Caorto builder, which builds the map. I will explain later what is the structure of this map. For adding the attribute to the map, we are using our vehicles with our sensors with a piece of software for map updater. And of course, the aim of all GIS is to be explored into vehicle during application. So as all GIS, it's based on node, segment, attribute. Node are related by segment, and attribute are affected to the segment. By our solution, we want to be simple. I will put two lines under simple. We don't want to be a competitor for existing, I would say, map editor or GIS solution. We wanted to answer our need and maybe the need of other person. So that's why we needed for debugging and simplicity to be a human-readable solution for the map, I'm saying. We want to have an instant access to the data. We want to have a lightweighted map to guarantee real-time functionalities. So we opted for text for ASCII files with hierarchical grid-like file system like the one into the Google Maps. So by talking about the map, we divided the world into 10 degrees squares and continue by a hierarchical way to divide it into small squares. This architecture, this structure of the data is reported to the file system. So we have the root folder, and we divided the structure into folder. Each leaves of the grid contain the node, the segment, and the attribute related to the region in this folder. Other functionality is that, in fact, this structure is reflecting the data contained in longitude, latitude data. So by a simple function, we calculate a path that we are going to use to access the data. Longitude, latitude is transformed into a path, and it is integrated into this hierarchy. For an example, one district in Paris for segment and node is about 5 kilobytes, and simple attribute is about 2 kilobytes, which assure a real-time manipulating. This is an extract of the node file, in which you have an ID of the node, and the GPS position of it, the segment, the ID of the segment, and the ID of the start node and end node, and the file for the attribute. Now, talking about the attribute that we have added to the segment. So there is the road name, the road type, and the number of lane. But for all advanced solution, for all advanced attribute, we want to add it to, we have a more granularity, so we want to add it to the lane level. And we wanted to have an exhaustive list of attributes, but we discovered that it's not exhaustive at all. I will explain it later. So beginning by the geometric attribute, like curvature, tilt, slope, and width of the lane. For signaling attribute, we added the traffic light with their position and with their type and size. The road signs, their position, and their type, of course. This is the vertical signaling. For the horizontal signaling, we mainly added the lane marker, which is with its type and its color. We add the arrow signals with their position and size, and the pedestrian crossing area, of course, with its position into the attribute file. And as a peripheral attribute, we add the pavement and the parking places left and right to the lane. As an example of the map explorer, this is some piece of code in which we are calling our object of the map. We are just given it the latitude, longitude, and it is given us the segment in which we are. So it project and filter position, it's map matched, and it gives us a view about the area in which we are. And for giving us the attribute, we are asking the attribute name, the road name, the speed limitation, and the vehicle orientation, for example. This is one of the first movie that we have done with it. In this application, we couple Caorto with Google Earth application. So we have here the registration of the recording of the camera, the same view with Caorto with the vehicle displacement, and at the same time in Google Earth. And we have now the name of the road, which is extracted from the map, the speed limitation, the distance to the next intersection. In the same way, it's another view in which we are changing view and viewing the next segment. So to obtain the attribute, we are using our vehicle, our instrumented vehicle, equipped with cameras, GPS, access to the canvas, and with our universal recording and playing software, RTMaps, which is let us record all kind of data and replaying it in real time. So for the map updater, we are using the video camera and GPS position to do a semi-automatic attribute collecting using the instrumented vehicle. So automatic vehicle estimation, automatic curvature estimation based on the history of the displacement, automatic road sign detection. We have a software for road sign detection, but we couple it with the human validation to say if it's correct or not. So automatic traffic light detection also with human validation. Automatic lane detection on video with lane width estimation. Semi-automatic road arrow collecting. So the human is designing saying that there is an arrow from this position on the video, and it's calculating its dimension. Semi-automatic pavement and parking place collection, and also for the pedestrian crossing area collecting. So it's done by human on the video. I will present now the usage of Caorto in several projects. It was very benefit for the project and for Caorto that it has been used in real project with real need. Then, for example, I will present two projects. One of them is Diva, which is a French project. Diva is Vehicle Infrastructure Dialogue for Road Safety. It's aiming at producing an innovative measurement method and tool for the road attribute. and to generate a recommended speed estimation and communicate it to each vehicle. In this project, we need a common spatial reference between the infrastructure side and the vehicle side, and Caorto was a solution for it. The Caorto system is integrated into the Divas system, and it is validated in 2 sites, in 40-kilometer site in Saint-Brieuc region in Britain, and on the Veolia buses, and on the SCPC test track in Nantes region. For this demonstration, for this experimentation, we added a new type of attribute that was produced in the project. I will cite the geometric visibility of the driver regarding its height, the microtexture and macrotexture attribute of the road. And also we have to add a new type, really new type of data, which is advanced speed attribute. It's the speed of the expert driving profiles, and some dynamic attribute like fog, rain, water level on the road, wind speed, temperature, humidity, which need to add also the timestamp, not also the value of the parameter, but also the timestamp, which is because it's a dynamic attribute, and the risky zone regarding the history of accident on road. Yes, it's not. Yes. The second project is PUMA, which is also a French project. The PUMA project is aiming at regulating traffic in the city of Rouen in France using V2I communication, by putting V2I communication into a vehicle and then to have a traffic control center to manage traffic. So the idea is to replace magnetic loop with a virtual magnetic loop. The vehicle is calculating its own trajectory duration between 2 PUMA spots, and it is communicated to a PUMA box. So for this project, we added three new type of data of attribute, which is PUMA spot, the PUMA box on the map, and the trajectory duration on each segment. Trajectory duration estimation calculating by the traffic center. It's okay.
Okay, thank you much. Thank you very much for your presentation.
Thank you.